Hey everyone, welcome to today's video. In this session, we are diving into a powerful caching solution in ASP.NET Core, Hybrid Cache. Hybrid Cache combines the speed of in-memory caching with the scalability of distributed caching. By leveraging this hybrid approach, we can achieve fast local data access while maintaining consistency across distributed systems. We will explore what Hybrid Cache is, its benefit and when to use it, and finally a practical example using iMemory cache for local caching and Redis for distributed caching. So what exactly is Hybrid Cache? It's a caching solution that merges two layers. In-memory caching, it means it stores data in the application's memory for ultra-fast access, and distributed caching stores data centrally so multiple applications or instances can share it. The magic of Hybrid Cache is that it gives you the best of both worlds. For frequently accessed data, it saves the data from the in-memory cache. If the data isn't found there, it falls back to the distributed cache. Here are some key benefits of using Hybrid Cache. First, it reduces latency by fetching data from the in-memory cache, which is much faster than querying a database. Second, it provides scalability because with a distributed cache like Redis, you can share cached data across multiple instances of your application, ensuring consistency and performance across the system. Third, it offers resiliency. If one cache layer fails, the other serves as a backup, preventing downtime. And lastly, it improves efficiency by keeping frequently accessed data local, which reduces network calls and boosts overall application performance. Now, when should you use Hybrid Cache? It's particularly beneficial in scenarios where performance and scalability are critical. For example, in microservices architectures, Hybrid Cache ensures that shared data is accessible across multiple services seamlessly. Similarly, in web applications with heavy traffic, it helps to offload the database by serving frequently accessed data quickly. Lastly, in APIs that handle repeated requests, Hybrid Cache significantly improves efficiency by reducing the need to fetch the same data repeatedly from a database. However, if your application doesn't operate in a distributed environment or doesn't require something like high rate performance, a single caching layer might be sufficient. Okay, now that we've covered the key benefits and when to use Hybrid Cache, let's dive into the hands-on part of this tutorial. We will walk through how to implement it step by step, covering everything from setting up the local memory cache with iMemory cache to integrating Redis for distributed caching. So without any more delay, let's jump into the tutorial and see how we can put Hybrid Cache to work in a real-world scenario. Okay, before jumping into the code, let's first talk about Redis and Docker, which we will be using for our distributed caching layer. As you know, Redis is an excellent choice for distributed caching. It allows us to share cache data across multiple application instances, making it highly scalable and efficient for distributed systems. To set this up, I use Docker, which makes managing environments and dependencies incredibly simple and lightweight. Specifically, I've set up a Docker container named Redis container for this purpose. This container runs Redis, providing the distributed cache functionality for our project. Now, within this container, we have the Redis 7.4 image, which is the engine that powers our caching operations. Redis is fast, reliable, and well suited for scenarios where we need high performance data storage for frequent reads and writes. Also, if you don't want to use Docker, you can also install Redis directly on your machine. On Linux and macOS, it's as simple as using a package manager like apt or brew. For Windows, while Redis isn't officially supported, you can use WSL to install it, or rely on tools like Memory or Chocolatey for a more Windows native experience. Direct installation can be convenient if you don't want the extra layer of Docker, especially for simpler setups or environments where Docker isn't available. Now that we've covered Redis setup options, let's dive into the project details and implementation. This project is built using .NET 9, so make sure you have .NET 9 installed. You can download it from the link I provided in the video description. Also, you'll need to upgrade your Visual Studio to version 17.12 to work seamlessly with .NET 9 and its new features. Now about the structure of this project. It's designed following the Kiln architecture principles. Kiln architecture helps keeps your code modular, testable, and maintainable by organizing it into layers like core, application, infrastructure, and presentation. If you are not familiar with Kiln architecture, don't worry. I've linked another resource in the description where I explain it in detail. Make sure to check it out. Alright, with that foundation in place, let's start implementing hybrid cache in this structured environment. Great. Now that we've covered Redis and the project setup, let's talk about the packages required for implementing this tutorial. These are essential for building a robust hybrid cache solution. First, you need to install Microsoft extensions caching memory. This package provides in-memory caching capabilities. It's the backbone of the local cache layer, allowing us to store frequently accessed data directly in memory for ultra-fast access. Then you need to install Microsoft extensions caching Stack Exchange Redis. This package enables us to connect and interact with Redis, our distributed cache solution. It uses the Stack Exchange .redis library, which is the go-to client for high-performance Redis operations in .NET. Alright, now let's talk about where all these dependencies and services are being implemented. All the caching logic, including both in-memory cache and Redis distributed cache, is implemented within the infrastructure layer. As you know, the infrastructure layer is where we implement external service and data access code that our application depends on, such as caching mechanism, database access, file storage, and external APIs. Okay, now that we know where to install the packages, let's move forward and set up everything in the infrastructure layer to make hybrid cache work efficiently. Okay, let's jumping into the code and start by talking about the iHybrid Cache Manager interface, which defines the contract for our caching functionality. As you know, I've created this interface within the core or domain class library. Here, I've defined an interface called iHybrid Cache Manager. It acts as a blueprint, meaning any class that implements this interface must define the methods we specify here. This method is the main method for our caching system. It tries to retrieve data from the cache using a key. If the data isn't there, it uses the provided factory function to generate the data, caches it, and returns it. A string key is a unique identifier for cached data. Factory is a delegate or function to fetch the data when it's not in the cache. And absolute expiration is optional. It specifies how long the data should stay in the cache. And finally, this method removes a specific key and its associated data from both cache layers. Now let's implement this interface in the Hybrid Cache Manager class. This is where we bring the logic to life. It uses iMemory cache for local and iDistributed cache for distributed caching. And this class is named the Hybrid Cache Manager. It implements the iHybrid Cache Manager interface, so we must provide definitions for the get or add async and remove async methods. This field is for local in-memory caching, and this one is for distributed caching. And also here is our constructor. Here I've created instances of iMemory cache and iDistributed cache via dependency injection. When you call get or add async method, it first checks the in-memory cache using try get value. If the data exists, it's returned immediately. If the data isn't in the memory cache, the next step is to check the distributed cache. The getString async method fetches a serialized string of the data associated with the given key. If the key doesn't exist in the distributed cache, it returns null, and we proceed to the next step. If the data is found, it's deserialized back into the original type T using a JSON serializer that deserialize. The data is also stored in the memory cache to make future accesses faster. Distributed caching is slower than memory caching, but still much faster than querying a database or external service. If the data isn't found in either cache, the method calls the factory function to generate the data. The factory is a delegate or a function pointer provided by the caller. It encapsulates the logic to retrieve or create the data, typically from a database or an API. Here we are creating the data via this string that we've passed to the API, but in a real situation, you likely connect to the database and fetch your data. Once the data is retrieved or generated, it is stored in memory cache, uses a set method to add data with a specified expiration time, and also distributed cache stores it using setString async with options for absolute expiration. Default expiration is 30 minutes if none is provided. And at the end, the data is returned to the caller. The get or add async method is the heart of the hybrid cache manager. It seamlessly combines the speed of in-memory caching with the scalability of distributed caching, ensuring efficient and reliable data retrieval. This method is designed to minimize latency, reduce repetitive data fetching operations, and optimize resource utilization. It prioritizes local memory cache for instant access, then gracefully falls back to the distributed cache if the data isn't found locally. When necessary, it regenerates data through the provided factory function, ensuring that even a cache miss is handled efficiently. And finally, this method removes the data associated with the given key from both the memory cache and distributed cache. Okay, so far so good. We implemented the hybrid cache manager class in the infrastructure layer, where we brought the hybrid caching mechanism to life. And now that we have a solid understanding of the hybrid cache manager and its implementation, let's move forward to the next step, registering our services and integrating the cache setup into the project configuration. We will also explore how these configurations connect to the broader application and how we can test this hybrid caching functionality. But first, let's dive into setting up the necessary services in our project. In the file service extensions within the infrastructure layer, we define a static class to centralize the configuration of services for dependency injection. Let's take a closer look at the add hybrid caching method in the service extensions class. The add hybrid caching method encapsulates all the necessary configurations for setting up both the in-memory and the distributed caching layers while binding them together with the hybrid cache manager. It ensures that all dependencies are registered and available for use wherever needed in the project. This line registers the in-memory cache with the dependency injection container. In-memory caching provides fast local data storage within the application's memory, ensuring quick access to frequently used data without involving network or external services. This could set up the distributed cache using Redis. The add stack exchange Redis cache method configures Redis as the distributed caching provider, and the Redis connection string parameter specifies the connection details. Redis allows us to share cached data across multiple instances of the application, making it ideal for distributed environments or microservices. Here we register our hybrid cache manager implementation of the iHybrid cache manager interface as a scoped service. Scoped services are created once per request, making this registration perfect for managing caching logic across a single request lifecycle. And now let's switch to the program.cs file in the presentation layer. Here the method add hybrid caching, which defined in service extensions, is called. The Redis connection string is retrieved from the appsetting.json file using the expression builder.configuration.get section to access the connection string value. Here the app settings.json file includes a section named Redis cache settings. Connection string specifies the connection details for Redis. This is the address of the Redis server. Localhost indicates the Redis server is running on the same machine as the application. This is the default port used by Redis. It can be changed in Redis configuration if needed, but it's common to use the default. If Redis were hosted remotely, you would replace localhost with the appropriate IP address or domain. Finally, here app.mapget method defines an endpoint for testing. This API endpoint takes a key parameter from the URL. The endpoint relies on the hybrid cache manager service to retrieve or add data to the cache. Get or add async method attempts to retrieve the data using the given key, and if not found, executes the factory function to generate the data, simulates a database fetch, and caches the result. Now that we've configured all parts of our hybrid cache mechanism, let's run the application and test our API to see how it works in real time. Here's how we will proceed. First, open the hybrid cache manager class and set a breakpoint on the get or add async method. This will allow us to observe how the caching mechanism works step by step. Specifically, we will see how data is fetched, stored in the cache layers, and retrieved during subsequent calls. Then start the application and run the API. The endpoint is located at this address. Replace key with a sample value, such as test key, for example, and hit the enter button. Watch the debugger hit the get or add async method. Since this is the first time we are calling this API with the given key, the system will check the in-memory cache, which will return false because the data hasn't been cached yet. It will then check the distributed Redis cache, which will also return empty since this is the first request. The factory method will generate the data, simulate a fetch, and store the value in both the in-memory and distributed caches. You'll see these steps executed in the code while the breakpoint helps you observe the data flow. Without restarting the application, run the API again with the same key and hit the enter button again. And this time, observe how the cache mechanism works. The system will first check the in-memory cache and find the data already stored there. Since the data is in memory, it will immediately return the cached value without hitting the distributed cache or the factory method. Notice how much faster the response is now compared to the first run, as no database simulation or network call is involved. Through this test, you can see how the hybrid cache leverages both in-memory and distributed caches. On the first call, it populates both caches with the data. On subsequent calls, it retrieves data directly from the faster in-memory cache, ensuring efficient performance. This simple test demonstrates the power of the hybrid cache mechanism and how it optimizes data retrieval in distributed and high demand systems. Now you can use real data instead of this sample data for storage. For example, you can call a method that fetches the data from a database and then stores it in both the in-memory cache and the distributed cache. And that brings us to the end of this tutorial on implementing a hybrid cache system with .NET 9. I hope you found it informative and helpful. If you'd like to explore the complete project, you can download it from my GitHub repository. The link is provided in the video description below. Feel free to check it out, clone it, and try it for yourself. If you enjoyed this video and found value in it, don't forget to like the video, subscribe to my channel and hit the bell icon so you are notified whenever I upload more tutorials like this. Thank you so much for watching, and as always, cheers.